Swayam Prabha. Digital India. Educated India.
So, let us now discuss the effect of the solid pile up in the liquid in the different growth formations during solidification of alloys. As you see, I have kept all these pictures, all the things, plots which I have drawn in the last lecture for your reference, so that you do not have to follow up again from the earlier lecture, and as well as I have drawn the phase diagrams for you to understand. So, we have been discussing on solidification of the alloy XP0, and I told you that the most realistic situation of solute profile is this one, the last one or the bottom one in these pictures. So, let us assume that we have a solute built up in this at the interface. So, if I draw that, I need to draw it to explain is, so this is my solute XP and this is the distance. So, what I have drawn is basically solid profile. This is KXP0, this is XP0, XPL, and this is XPE. Okay. So, this is, let me just draw it, KXP0 is here, XPL, and this is XPE. So, that is why they are coming higher, and this is XP0, and what I have done, let me draw a line here. So, this is, I am talking about intermediate case. Okay. So, this is the solid profile look like. Now, how can I use this solid profile to discuss about the different growth forms? Well, let us do that. Remember, this is composition versus X profile distance. Now, I can actually take composition in the liquid. So, suppose this is my XBL1, XBL2, like that. Okay, it goes on, it actually goes much, become flatter, later on XPL, N, something like that. Now, these compositions in the liquid will determine its liquidus temperature, obviously, because in the phase diagram this is liquidus, let us put it in color, otherwise it is very difficult to follow. So, this is my liquidus, okay, and this is my solidus, right, the green one. So, as you clearly see, the temperature, this is a temperature versus composition plot. That means, for any composition on these liquidus, I can determine the temperature. If I know the liquid composition here, I know the temperature here, that is the liquidus temperature. So, therefore, if I know the composition of this solute in the liquid, this is what is given by this profile, it looks like an exponential, I have given the equation also, it is exponential. So, I can actually measure composition at each point on the liquid, in the liquid, okay, I can see here, I can do that. And then I can actually plot these compositions on this axis, on the x axis of these, on these phase diagram. So, by doing that, I will know what are the liquidus temperatures. So, as you can clearly see, when the liquidus is very high, temperature will be low, right, because there is at these interface that the composition is very high, there is a spike, then slowly goes down. So, therefore, at the interface temperature will be very low, because as you see how the liquidus composition is high, temperature is lower. So, as the composition increases and finally it becomes same as XB0, the temperature goes down, right. So, therefore, if I plot now here x as a function of TL. TL is my liquidus temperature. So, what will happen? Okay, I am drawing for the liquid, solid there is no liquidus temperature. So, obviously it will be very high, very low here because this composition is low, and let us mark this as this point, and then it will slowly increase, right, slowly increase. This is what it will look like, because composition is high, liquidus is low, composition is lower, liquidus is higher. That is very simple, that is a direct correlation. So, that is mass liquidus. Now, this is my interface, right. The question is this: if this interface develops, suppose a protrusion like this or another protrusion like that, whether these protrusions will grow or not. Okay, if they do not grow, the interface will move like a flat. If they grow, interface will break down and form dendrites. That is what will happen. So, under what condition they will grow? Obviously, this is my equilibrium liquidus temperature, right. That is what I have done, equilibrium liquidus temperature. Why it is equilibrium liquidus? Because we are drawing it from the phase diagram, and phase diagram tells you equilibrium information. Actual situation may be different. So, this is tells you, because this is TXL versus distance plot. So, this any point on this curve will tell you the slope or the gradient, temperature gradient in the liquid, any point on this curve, because this is a plot between temperature versus x is the distance. So, now actual experimental conditions may not be following, or it will not follow the equilibrium situation, because in actual experimental condition we may be extracting heat faster, we may be cooling slowly, we may be doing many other things. Actual experimental conditions actually vary. So, therefore, in actual experimental condition the temperature gradient in the liquid can be modified, can be changed. So, suppose if I impose certain experimental conditions and temperature gradient in liquid looks like this. This is my experimental condition, this is equilibrium TL, this is my experimental TL, TL experiments 1. Under 1 experimental conditions, my liquidus temperature looks like that, or basically temperature gradient has this much value. This is basically given by this slope. Now, if I have such a kind of situations, that means the actual temperature gradient is higher than the equilibrium temperature gradient. So, if there is any kind of a protrusion forms in these, they will melt, because temperature is higher, actual temperature is higher than the equilibrium temperature, and because of that, if there is at all any kind of a protrusion or any kind of a things form in the interface become little bit jagged, just like the ones which I shown you in the last lecture, they will melt back, they will be melt back and the interface will remain flat. So, therefore, this is the experimental condition 1 in which interface will remain flat, it will not be at all forming any kind of features. But suppose, okay, let me draw this is as a white line so that you do not forget, this is my first condition. Suppose I have a little other experimental condition in which the slope or the gradient is like this. This is TL experiment 2, correct. As you see here, in the region from this part to this point, okay, the liquidus temperature, actual liquidus temperature of the sample, that is the experimental TL experiment 2, is lower than the equilibrium liquidus temperature. So, because temperature is lower, the liquid, if there is a solid protrusion forms here, okay, if solid protrusion form here like this, they will feel comfortable, they will not melt back, they will feel that they are undercooled. Why they are undercooled? Because temperature is lower than the equilibrium liquidus temperature. Remember, anything below this equilibrium liquidus temperature, solid can remain present, because this is the region between alpha plus liquid. Anything above, it is only liquid. So, above this temperature liquid can only remain, below this temperature solid and liquid both can remain. So, because the temperature here is lower than the equilibrium liquidus temperature, because of experimental conditions, we are going to develop this kind of serrations or this kind of features on the surface, and these features will then grow as the time goes on. These features will become bigger, much bigger. And finally, these features will become dendrites. Okay. They will form dendrites. So first interface breaks down, we form cells. Cells do not have any secondary arms or tertiary arms. Then secondary or tertiary arms forms, they become dendrites. That is what happens in actual practice. So therefore, formation of alloy dendrites is something to do with the undercooling because of composition or because of constitutional, and this theory is known as constitutional undercooling. Theory. This has been described as a constitutional undercooling theory. So therefore, without even going into details of the different aspects, we can simply explain why such a kind of things, such dendrites and cells form in the alloy dendrites. But this theory always have two problems. This theory is very simple and elegant also, very elegantly explains things very easily. That whenever I have actual temperature gradient is lower than the equilibrium temperature gradient in the liquid, we will have serrations formation on the surface interface, and this protrusion or serration, whatever you call, they will grow into the liquid, and that is how these dendritic growth forms will arise. But in undergoes two important things. One, the gradient is mainly because of compositional. So if suppose I have a pure metal, I do not have any solute present, there will be no compositional gradient developed, and that means all the pure materials should go by a flat interface, there will be no dendrites. But as you have seen in the last lecture, in pure metal also we do see dendrites, and these dendrites mainly because of the temperature, thermal effects, not because of compositional effects. That is the number one drawback of this theory. Second drawback, which is more important, whenever you have a flat interface as compared to a flat one, the curved one or cells or dendrites will have a larger surface area or interfacial area, and this interfacial area change will lead to change of the energetics of the system. If I have to add total energy of system as a P energy decrease because of the liquid to solid transformation, that we have seen in the earlier lecture also, plus the energy because of this interface, then only I will find the actual things will not be so simple. But this theory completely undermines the effect of interfacial area. They never consider the interfacial area at all. So therefore, this theory cannot talk about the scale of microstructure, whether smaller size dendrites will form or bigger size dendrites will form, they cannot discuss, because they have not considered the effect of interfacial area. So these are the two basic problems of this theory, although this was discovered long back 1954, but this has this problem, that is why this theory was discarded later on. In fact, in 1960s, 1963, 64, 65, this theory was discarded, and people have described a new theory, which I will just give a glimpse of that. I will not discuss much about this, because that is a part of solidification, that is not part of the phase transformation. Okay. So instead of thinking of a constitutional undercooling, the main reason behind the dendritic growth, we can simply think that I have a flat interface initially, okay, this is solid, this is liquid, and there is always some fluctuation present in the interface in terms of temperature, in terms of composition. Temperature may not be uniform across the interface. Interface is microscopically not small, okay, maybe thickness is small, but the length is not small. So there will be always some fluctuations of the temperature or composition, or maybe some other elements like oxygen, nitrogen in the environment. These fluctuations can lead to interface perturbed. Interface will become perturbed. That means I can develop some sinusoidal perturbations on the surface. You see, this is a sinusoidal curve. You can also have co-sinusoidal or any other kind of perturbations. Now the question is this, fine, because of compositional change or temperature variation across the interface, certain kind of perturbation has developed, acceptable, understandable. Now question is that under what condition these perturbations will grow? They have two choices, either this perturbation will vanish, the interface will remain flat, or these perturbations can grow and form again cells and dendrites. So that was done much later, and that explained why dendrites form and why these growth forms are present in the actual solidified materials. Well, then there are many other things which I will not be able to discuss you, because that takes a lot of time, but this theory is well known, okay, and this theory is there in the literature, so you can, even in the books also you can read it, even in this book also it is there, talks about this theory and discuss about that. So before I complete this today's lecture, let me just introduce you a new things which we will discuss today as a part of liquid solid transformation, which is very widely present in the different alloy systems, that is the eutectic solidification. Remember, we are all discussing about single phase solidification so far, whether it is a pure metal or it is an alloy, we are only discussing about single phase solidification, but multi phases are also very important. As a part of your curriculum, multi-phase means only eutectic solidification is present. So I will spend about 5-6 minutes today and the next lecture on eutectic solidification before we simply complete this part of the course on solid liquid to solid transformation and move ahead for the other things. So eutectics are very common in the actual practice. We use many eutectic alloys, right? We use lead tin as a solder material, we use aluminum silicon as a cylinder blocks of the engines in the cars and the trucks, or we use cast iron. These are all eutectic alloys. So therefore it is important that you have some idea how eutectics solidifies in the these materials. Obviously eutectics are much more complex than we think about it, than we actually suppose, but they are much more complex. Actually the eutectic solidification can vary from one system to others. So we will be not able to discuss in details that much, that whether eutectic solidification in aluminum silicon alloy is distinctly different from the cast iron or not, that is not possible for me to discuss, but I will give a generalized theory of eutectic solidification so that you have some idea about it and you can then build on it later on. As you know, the classical eutectic phase diagram is little bit different from what I have drawn. I have also drawn a part of the phase diagram. So eutectic phase diagrams are actually very widely present in the literature. You will find many phase diagrams where eutectic is widely present. A simplest eutectic phase diagram with two terminal solutions is like that. So alpha beta are the two terminal solutions and eutectic is basically the lowest melting solid in this phase diagram. As you see here that both the liquids is going down and they are meeting at a point whose temperature is lower than the melting temperature of pure A and melting temperature of pure B. So therefore eutectic reaction is basically liquid going to alpha plus beta. When at the temperature T it happens, the T is basically given by this line. This is an invariant line, we know that. So eutectic is a very classical phase reaction. So what does it tell? This particular reaction tells you that from the liquid two solid phases simultaneously form. Two solid phases are directly forming together from the liquid. Depending on how the solid phases will be distributed in the microstructure, you can have different kinds of morphology. The classical one which is present in the lead tin or other alloys is basically lamellar. I will show you all these pictures in the next lecture, lamellar. Okay. You can also have rod type, that means one of the phases will be like a rod, either alpha or beta, whosoever volume fraction is little lower. You can also have spiral or acicular eutectic or globular. Spiral eutectic is found in magnesium zinc system, acicular is aluminum silicon, and globular is found in copper oxygen, Cu2O. So lamellar is basically lead tin, rod is basically nickel aluminum or niobium silicon. There are many other morphologies, I am not discussing about that. The important ones are these. You can also have eutectic with Chinese creep microstructure. So those are actually very special cases, but these are actually routine normal things. Normally you find most of the eutectics are lamellar type, like lead tin is one classical example, or rod type. Normally rod type eutectic forms in one of the phases is basically volume fraction is low. You can also have a spiral if suppose one of the phases, both the phases have different thermal expansion coefficients, then you have a spiral eutectic. Very simple, if I have a metallic rod, okay, of suppose say two metals, and if I start heating it up, because of the difference in thermal expansion coefficients, one will bend over the other, and then is the one, that is the way spiral eutectic forms. You can also have acicular eutectic. One of the eutectic phase is fibrous, like silicon, in aluminum silicon is basically fibrous, but the aluminum is a continuous phase. You can also have a globular, like one of the phase Cu2O is basically forms like a globule in the continuous matrix of Cu. So these are all very classical things which are found in the literature and the books. I will show you some of these slides in the next lecture, and then I will try to develop a theoretical foundation where you can actually use the theories to explain the formation of eutectic.